Okay, I'm making this recording to get you started in section 2.3 because I would prefer, I kind of like to, with my experience teaching calculus, I found that introducing the rules for working with limits, rules for evaluating limits a little bit differently than your textbook authors do works better for me. So I want to kind of start you off slightly differently. You're still going to need to read section 2.3, and you're still going to need, obviously, to work the examples that are in your text and work on your homework. But I think this little 15 minutes or so of extra stuff that I can give you right here will help you. I want to start you thinking about limit techniques just a little bit differently to begin with. And we're going to start by thinking about limits of our two most basic types of functions. The first one is the constant function. So what I'm suggesting here is that we consider a function f of x, dadgum, come back. There we go. F of x is equal to some number c. And if we are considering a limit as x approaches a of this function, I hope that it wouldn't be too much of a stretch for you to recognize that the function value is getting closer to c as x gets closer to a, because f of x is equal to this number c no matter what value of x we plug in. So if we're thinking about substituting numbers closer and closer and closer to the value a, all of our y values are going to be c. So the limit of a constant is the constant. It's very, very simple. The next function we want to take a look at is the identity function. Let me scoot this down just a little bit. Again, the function we're considering here is f of x is equal to x. And when you consider the limit as x approaches a of that function, what you've got to ask yourself is, what value is x getting closer to as x gets closer to a? And that's got to be a. So when you take a limit of just the very basic identity function x, when x gets closer to a, your function value is getting closer to a. Now, the remaining rules for working with limits come straight from your textbook, the limit laws. It's actually Theorem 2.3 in your text. And I'm just going to run through these very quickly and talk to you a little bit about each one. Give you some hints and some ways to think about this that I think make them a little bit easier to understand. All right, what we're looking at first in the sum rule, or the sum laws, is we have a limit of a sum of two functions, f of x plus g of x. I think many of these rules are much easier to remember if you remember them in words, rather than try to memorize that mathematical notation that's right there. Think of what this is saying in words. The limit of a sum, okay? So here's the limit of a sum, here's our sum, is the sum of the limits. So you take the limit of f of x, you take the limit of g of x, and you add those two limits together. It makes it a little bit easier to think about. The limit of a sum is a sum of the limits. Okay, and I need my pen back. There we go. Okay, moving right along. Very similar rule for working with a difference of two functions. If you have a limit of f of x minus g of x, you can take the limit of f of x, take the limit of g of x, and subtract the limits. So a limit of a difference is a difference of limits. The constant multiple rule is next, and we've got some constant number c multiplied by function f of x. What this rule allows you to do is to pull the constant out in front, evaluate the limit of just the function f of x, and then multiply by c. So in each of these cases, what we're doing is we're taking a, complicated really isn't the right word, but we're taking a more complicated function and breaking it down into smaller parts so that it is much easier to take the limit and then put the parts back together to get your answer. The product rule Okay, if you have a limit of a product, that is going to be the product of the limits. So again, you can take, if f of x and g of x are multiplied together, you can find the limit of f of x, find the limit of g of x, and multiply the numbers together. Limit of a product is a product of limits. We have a similar rule for a quotient. The limit of a quotient is a quotient of limits. And then this extra stuff here is basically giving us, you know, anytime you have a fraction, anytime you have a quotient, you've got to make sure you're not dividing by 0. So this quotient rule only works if the limit of the denominator is some number other than 0. If you end up with a 0 for that bottom limit, then you've got to go about this in a different way, and you're not going to be able to evaluate it using just the quotient rule. Power rule. I kind of think about this the same way I do the constant multiple rule. I've got a limit of a function raised to a power. I can take the limit of the function and then raise it to the power. So I'm taking the power outside the limit. Sort of like I took the constant outside the limit in the constant multiple rule. And then finally, the last rule is sort of a specific version of the fractional power. It's a specific version of the power rule. The difference here is that our power is a fraction, and there are a couple of things we have to consider. First of all, this f of x has to be greater than or equal to 0 for all x near a. What that's telling me is that the limit as x approaches a for f of x has got to be greater than or equal to 0. It's got to stay positive. Can't have any negatives if m is even. Now look at where m is. M is the denominator of the fraction that is our power, which means we're talking about an nth. It's not really a word, but you understand what I mean. We're talking about a root, an nth root. Can you take, say, a square root of a negative number? No. So this fractional power rule, basically all this extra stuff is telling us that, and of course our fraction needs to be in reduced form. But basically this is saying that you can use this power rule only if it makes sense. If you end up with a square root of a negative number, you have no limit. You're not going to be able to evaluate the limit that way. If you end up with a fourth root of a negative number, you cannot take an even root of a negative number. So just be careful. So again, basically all of what these rules do for us, let me skip ahead to an example, very simple example that I want to work for you. All these rules do for us is allow us to substitute to evaluate a limit. Okay, and when you get to Theorem 2.4 on page 67 of your book, that goes into a little bit more detail there, but basically what that theorem is telling you is that substitution is okay as long as nothing bad happens. And by nothing bad, I mean you can't have division by 0. You can't have an even root of a negative number. As long as nothing weird happens like that, it is okay for you to substitute. So looking at this limit two different ways. If I apply the limit rules, the first thing I see there is a difference. So I would break this down to be the limit as x approaches 3 of the term 1/2 x minus the limit as x approaches 3 of the term 7. Then my first limit there has a constant, so I can pull the constant out in front and look at 1/2 times the limit as x approaches 3 of x minus, and I just bring down the other limit. Now notice, after that first step I could go ahead and evaluate the limit as x approaches 3 of 7, but I want to wait and do all my limit evaluations at once. And notice that I also write down the limit as x approaches 3 in each step. That's important. You've got to write that limit notation until you actually work the limit, which we're going to do now. According to the second rule that we looked at earlier, the limit as x approaches 3 of x is 3. according to the very first rule for evaluating limits that I gave you, the limit as x approaches 3 of 7 is 7. So we're looking at 3 halves subtract 7, which if you rewrite 7 as a fraction, you'll end up with negative 11 halves. So if I worked the same problem using substitution that I've kind of told you is okay now, what we would be looking at, let me write the problem down again so we can see it. The limit as x approaches 3, the function is 1/2 x minus 7. Okay, using substitution, I can write not 1/3, that's wrong. I can write 1/2 times 3 subtract 7. And then you're looking at 3 halves minus 7, which is exactly what we had before, negative 11 halves. So you definitely want to make sure that you read through the text. I have not covered everything, but I just sort of wanted to introduce working with limits and working with the limit rules a little bit differently. You are now ready to go on to the rest of the assignment.